Good afternoon, or morning, or evening, depending on the country you are joining us from. A very warm welcome to everybody to this webinar, Sustainable Fast Charge for Future Vehicles and Transport, Inductive Technology for Electric Vehicle Charging. Let me introduce myself. I am Maria Lopez from Tecnalia, the Division of Industry and Transport, Automotive Business Unit. And due to the tight schedule, I will use just 1 minute to thank the speakers and organizers of this dissemination activity within the European Union Framework Program 7 Project FastinCharge, and hosted today by BATERY and Tecnalia, from where we are webcasting today. We have with us a panel of relevant speakers, members of the FastinCharge project consortium, who will give us valuable insights and perspectives from the different aspects of the fast inductive charging of electric vehicles and related issues. We believe that innovative fast charging solutions are key to facilitate the implementation of electric vehicles in the urban grid and to broaden the utilization by the large public. So let's go ahead, and with the agenda we have 6 10-minute presentations, followed by a final 15 minutes open discussion session. Don't forget to follow also in Twitter the hashtag FastinCharge, where you could post your messages. So, following, I am pleased to introduce the first speaker, Mr. Luca Marengo from CRF Italy, who will talk us about the vehicle aspects of the wireless charging. Please, Luca, the floor is yours.
Thank you. My name is Luca Marengo from the Fiat Research Center, and I work in the electrical electronics department, particularly in the area of the alternative propulsion systems. In the next minutes, I will try to give you some hints about the challenges behind the integration on vehicle of the wireless charging devices. About the battery electric vehicles, the main issue that we have are that we have a range anxiety that is felt strongly by the users because of the limits of the battery. We have batteries that have limited energy capacity. The infrastructure, the second point, that is a drawback at the moment, because we have a few charging stations that cannot sustain the implementation of a wide deployment of the electric vehicles. Then we have the charging time. At the moment, we need fast and high-power chargers in order to be sure to recover the charge of the battery in a few minutes. That is not possible to be done at home for obvious reasons. And the most important thing from our point of view is the reduction of the cost of the batteries that is affecting strongly the electric vehicle cost overall. So that said, we can look at the positive aspects of the wireless charging. First of all, it should allow the reduction of the battery pack size. So in the end, we can reduce the weight and the cost of the battery pack. It should be easy to operate for any user and robust with respect to the conductive chargers. Then we have also potential outcomes from the extension of this working mode to the dynamic charge while driving. And moreover, we have different scenarios that can be implemented in order to improve the widespread diffusion of the electric vehicles on the market. A wise implementation cannot neglect the cost saving and, first of all, also from an electric vehicle point of view, the weight saving. So we need devices that are light, that cannot add weight with respect to the conductive charger that is the main device competing with the wireless charging. If we look at the negative aspect that we can see at the moment in the implementation of wireless charging, first of all, we need to find the right trade-off for the positioning systems that should be compliant with the state-of-the-art on the market about the driving assistance systems. And the implementation of this technology should follow a parallel path with respect to the wireless charging positioning systems. Moreover, we have the integration of the wireless charging systems that is, from the car maker point of view, should be a plug-and-play approach in order to minimize the effort in integrating this kind of device mechanically and electrically on the vehicle. And Also, we need to be sure that this kind of system is safe from a compatibility point of view with respect to the existing items and devices on the vehicle. We mean the current and voltage with respect to the battery system and the electromagnetic compatibility and the communication with the existing networks on the vehicle. Other negative aspects that can be seen at the moment are the interoperability between the installed secondary coil and different wireless charging stations. From a car maker point of view, we need to understand that our secondary coil is able to operate with different parking slots, with different charging stations. Otherwise, it is not possible to think about a widespread adoption of this kind of technologies. Moreover, the data cost of the vehicle equipped with a wireless charger is at the moment possibly higher than what can be done with conductive charger alternatives. We need also to take into account that the device efficiency in principle is slightly lower than the conductive charger alternatives. It can be improved, and this could be definitely something in help in order to achieve a widespread application of this technology. And the most important aspect from a user point of view is the safety, not only with respect to the electromagnetic compatibility, but also with respect to the user itself and the effect of objects that can intrude the air gap between the devices operating, that are the secondary and the primary coils. The last aspect is related to the dynamic charging, that from our point of view respects some weak spots. For instance, we have some concern about the air gap that should be consistent with the safety distances from the ground plane in order to avoid the destruction of the device in presence of manholes and similar problems with the road. And the management of the charger is also important in order to be integrated, implementing a control loop that is safe and reliable with respect to the charging station. And in the end, it is also important to take into account the possible intrusion in the air gap of metallic, organic, or even living things. I mean, the typical example of the cat passing on the road while the car is approaching the wireless charging item. And we need to address all of these issues in order to be sure that the implementation and the adoption can be safe, not only from a vehicle point of view, but also from user and third-party players involved in the application of this kind of devices. From my point of view, this is all. So I don't know if we can switch to the next one.
My name is Reda El Ajaji. I'm a research and development engineer, and I'm working in DBT's design department. We are the project coordinator of this project, and the main features is the starting date. It was 1 October 2012, and the end of the project it will be in 30 September 2015. The total budget of the project it's about €2.5 million, and maximum contribution of the AC of the European Commission is about 69%. The partners of this project it's Technical University of Gabrovo, Automotive Cluster West Slovakia, BADS, DUE, Oral Quality, and ICCS, Technalia, and CRF. The objectives of the project is to develop and demonstrate a complete charging infrastructure in order to address consumers' acceptance of electric vehicle by getting rid of the autonomy issue, test its implementation, and assess its easy feasibility. optimize the energy delivery to station and its interaction with the grid and the vehicles. Study the impact of its integration in the urban environment to foresee eventual problems that will occur in the frame of real integration. And the solution will be integrated in one vehicle, Iveco daily, and demonstrated in the way. The main expected results, it's the development of one primary plate to be integrated to one vehicle, the development of 2 charging stations for static and on-road to be integrated in Dewey, and the optimization of the energy management system, and the demonstration of the efficiency and viability of the solution in real life conditions. There are 7 work packages of this project. The first work package is for the specifications. The work package 2 is for the development of static and on-road fast inductive charging infrastructure. The work package 3, its objective in this work package is development of integration solutions like power supply from the grid, energy management, and data security. The work package 4 is for the integration and the prototyping and testing. Work package 5 is for the demonstration and impact impact analysis. Work package 6 is for the disseminations, and work package 7 is management. For the work package 1, the data is DBT, and there are two deliverables. The 211 functional specifications, which is who is DBT, the task leader of this deliverable, and also for 212. The leader of work package 2 is TUG. Work package 3 it's ICS, and the CRF it's who is the leader of work package 5. Dewey, it's the leader for work package 5, and RCWS, it's the leader of the work package 6. Yes.
Hello, good afternoon. My name is Stefan Milchev. I am member of Technical University Gabrovo, Bulgaria, and our team is responsible for inductive power transfer of energy. For this case, inductive power transfer technology is our basic technology. From physical point of view, inductive method of energy transfer can be defined as an open transformer with resonant magnetic coupling. This transformer has 2 sides. The primary side is so-called transmitter, and the secondary side. In some cases, the secondary side contains several secondary parts, and they are known as a receiver or pickup sites. On this slide, we can see some basic constructions of IPT transformer modules. The difference between 2 constructions is regarding air gap. between coils. Small air gap groups and large air gap groups constructions. Small, that means value between 5 and 10 millimeters, and larger is a larger group of transformers. Our FastinCharge IPT concept for charging of electrical vehicles has the following three very important challenging requirements. The first one is that we have to develop fast static charging methods of vehicles, of batteries. The second development requirement is that we have to realize not only static but on-road charging station, charging infrastructure. And the second basic requirements is that in these two cases of charging station, we have to use identical technical solution, taking account different models like primary, secondary coils, power electronics models, and so on. On this slide, you can see technical specification of FastinCharge IPT models, taking account for previous basic requirements. I would like to put your attention about the following data. We output power of high-free secondary coil has to be 30 kilowatts, and charging time has to be implemented from 20 up to 30 minutes maximum. These two parameters define FastinCharge solution for our development. And another parameters are very important too. Dimensions, of course. Very important parameter here is the distance between coils, misalignment between coils, because taking account these parameters, we started to develop and to design all electronic and IPT models. The first step of the project development is a choice of the location of IPT modules in AV, taking account that we have to realize static and dynamic charging with identical technical units. We have no choice in our case. The secondary coil is located on the water of our demo unit. And the second step is to determine many electrical and mechanical parameters through numerical simulation of electromagnetic fields and so on. On this slide, we show one of our first IPT primary coil transformer. On the left side, you can look the construction. On the right side is a real picture of this coil. in this table below are main parameters, mechanical parameters. As I mentioned before, simulation of the electromagnetic fields is one very important step of our development works. And here you can see some results. Simulation of magnetic fields distribution between primary and secondary coils without aluminum shield. On the next slide, you can see the impact of aluminum shield to the distribution of magnetic field. These results are very important when we have to take final decision about the final construction of the primary coils. And on the next slide, again, distribution of electromagnetic fields when there is misalignment between coils. Because in a real situation, this misalignment is practically, it will be possible to have this practical case. Okay. Here you can see the total construction of our primary coil. I would like to pay your attention of components. One, this is protective layer of the primary coils, and this protective layer has not to contain metal. For this reason, basalt fibers are used because these basalt fibers simultaneously guarantee mechanical properties of this layer, what is very important. In this slide, you can see a real picture of primary coils. Main components of this primary coil are magnetic ferrite cores and leads wire turns. These two elements are main subject of our development work. Matching primary electronic circuit to the primary coil is very important from electrical point of view, and that's why we present this circuit here. On the secondary side, the electrical circuit is AC/DC functional electrical circuit, and here on this slide there is results of final results of design of AC/DC module, which is located like that. And on this slide, you can see our FastinCharge concepts of on-road infrastructure. In our project, 4 primary coils are used. And on this picture, there is some our results regarding what distance have to be between primary coils, and what is very important, power distribution of energy. This result is used for a design of power electronics and simultaneously for demand management system of grid energy. Here you can see the real picture of our first laboratory prototype in this mock-up. In this mock-up, on the left side, you can see that there is 4 primary coils and 1 secondary coils. That means through this mock-up, we were able simultaneously to investigate start in the static and FastinCharge solution. On this picture you can see a testing bench of battery, which was used for final testing of IPT modules. Overall view of testing equipment. Here we present in this slide what are main modules of charging station. Modules, final design of primary side in inverter modules, matching capacitor, matching trafos, control units, and so on. And here are our main conclusion of our development work. Thank you for your attention.
Hello everybody, my name is Aitor Bustillo from BATS and I will present you our system developed especially for this project in order to get a mechanical system to approach the 2 coils during the process of charging of the batteries. To start with the development, we gathered all the requirements from all the other partners, all the other parts of the project, mainly the IPT module, the vehicle, and the infrastructure. For example, dimensions of the coils, weight of the coil, of the secondary coil, which is on board, the air gap between coils to be achieved. Regarding the vehicle, the space available on board in order to accommodate the system, the maximum speed when charging of the vehicle, and regarding the infrastructure, the road features like such as asperity, obstacles, and other ones. The next slide shows the final design we got in order to fulfill all the requirements the other partners required to us. There are different components, such as a rolling system, which transports the secondary coil, and then there are some other parts which provides the movement of the system in order to be well positioned on board when it is not in a charging position. Once we have the design clear and approved by all the partners, we have started to manufacture the first prototypes. We are in process of validate all the prototype, and in order to accomplish the whole validation, we have made different steps. We have accomplished the mechanical integration, we have made electrical and electronic integration, control algorithm development, and nowadays we are with the test operations. Here we can see a sequence of the system showing how the system works. You have seen the up movement when the car is supposed to have end or finish the charging operation. The system is able to recover all the secondary coil and to be integrated in the vehicle. Thank you very much for your attention.
So in this slide we can see the design of the charging station for our project. The dimensions of the station for the height is 840 millimeters. For the width, it's about 390 millimeters, and the depth is 516 millimeters. The charging station contains the following components: the main controller of the station, which enable to control the charging with the communication of the AV. It's also enabled to communicate and guide the user to the charging process. Contains also the identifiable lighting of the station, LED indicator, which enable the users to easily identify the status of the station. Contain also the energy meters, the electrical protection, like the main breaker, overcurrent, and voltage, charging coil, and the temperature and humidity sensor. Contain also the communication via GSM or GSM network or Wi-Fi. The station should be it's designed in a way to enable simplicity of use, managing of charging process. In case of fault of charging process, the station status is automatically changed into not available with appropriate display. Resistance or to bad weather, easy access for madness, and it's also enabled for the configuration interface of the charging station, and for the remote or local parameterization, and also for the monitoring of temperature inside the charging station. The pictures illustrate the overview of the cooling system. So the cool fresh air enters from the below of the station, and it's down in the station by 7 fans. The station contains some models from TUG, like the inverter and the compensation model, and also the modular design for the goals to modular design, easy maintenance, and high power density factor. The existing problems is the construction of charging station is slightly modified. For the dynamic charging, we will use the same design for like static charging, and we'll have 4 coils on the globe. Please, can you pass on?
Hello, my name is Ioannis Karakitschios, and I'm from the National Technical University of Athens and the Smart RU Research Group led by Professor Nikos Hatziargiriou. And I'm gonna have a presentation today about the fast inductive charging needs and the energy management system developed in the scope of this project. The first part of the presentation concerns the definition of the fast inductive charging needs. Inductive charging is a newly developed technology, therefore there is no operational experience concerning its demand profile. However, the operational behavior of fast stationary inductive charging will resemble the respective one of fast conductive charging. After processing real data on fast conductive charging stations, the following 2 parameters are defined. The first parameter is the hour of the day that the charging event is expected to occur. And we can see in the first figure that all of the charging events occur between 7 AM and 9 PM, while a peak in the EV traffic can be observed in the morning and middle day hours. The second parameter to be defined was the duration of each charging event, and we can see in the second figure that most of the charging events last for 15 to 30 minutes, while none of them has a duration longer than 1 hour. Now, in case no inductive charging stations are installed in the grid, as we can see in the blue line in the figure, a significant peak can be observed in the EV demand. If the peak of the grid demand occurs at around the same time with the EV peak demand, conventional conductive charging could raise operational challenges to the system operators. Fast inductive charging implementation could shift the high EV demand from the evening towards the middle day and morning hours. In fact, in a scenario where a significant percentage of the drivers daily charge at fast inductive charging stations during the day, quite a considerable decrease can be observed in the evening demand, as we can see in the green line in the figure in the slide. However, the deployment capital of inductive charging infrastructure and the electricity cost are issues that should also be considered. Now, drivers using fast inductive charging solutions during the day may also plug in their vehicle when they return home, receiving a percentage K of their daily energy needs from home conductive charging. An increase in the evening demand shall be expected in this situation, as we can see in the figure. The amount of increase depends on the percentage of the daily energy demands received from home conductive charging. We can see that a considerable increase is anticipated in case the relevant percentage is quite high, as we can see in the green line of this figure. However, even in this situation, fast inductive charging is able to shift a significant amount of the EV demand away from the evening towards the middle day and morning hours. The second part of this presentation concerns the energy management system developed in the scope of this project. Inductive charging should be considered as a service of charge as fast as possible. Inductive charging technologies will offer EV owners the option of fast charging in an increased energy tariff compared to conventional home conductive chargers. EV owners will pay more only in case of emergency charging in order to be able to continue their travel. Since there is no time flexibility in case of inductive charging, the availability of its inductive charging infrastructure should be defined a priori based on social and technical criteria in order to prevent network operation disturbances. The scope of the smart energy management system is to make EV owners aware of the availability of its inductive charging spot that can serve them without causing any disturbance in the grid operation. Therefore, a user interface is developed so as to inform EV drivers for the location of the available inductive charging posts. The user interface is an applet that can be installed in a tablet or a mobile phone. Furthermore, the user interface will provide an estimation of the remaining time that the unavailable inductive charging posts will remain busy. Based on this information and according to the EV driver's travel needs, which are the direction, his or her direction and the energy requirements of the vehicle, the driver will be able to choose one of the available inductive chargers. The EV drivers will also be able to book a specific inductive charging post and determine the desired charging time. The overall outline of the energy management system is presented in this figure. When the EV is appropriately placed over the primary inductive plate and the EV owner requests for charging, the maximum charging rate is defined by the nominal apparent power of the charging infrastructure. The monitoring center, which is responsible for monitoring the operation of the charging post and recording the respective consumption, can reduce the maximum allowable charging power exchange between the grid and the charging post. The current consumption of each charging post is stored in a central database placed at the EV supply equipment operator's system. And when an EV owner needs to charge their EV battery, he or she will drive to the nearest available charging post. However, the closest fast inductive charger might be busy and the EV owner will have to find the next closest charging post. For this reason, the user interface module makes EV owners aware of the available charging posts, as well as the estimated remaining time that busy charging posts will become available again. Therefore, based on their charging needs, their travel direction, as well as the location of available charging stations, the drivers can reschedule their driving route to the desired destination in order to reach the most convenient and available charging station. Furthermore, EV owners will be able to book specific time slots in a charging post by defining the time of arrival and departure. Also, the decision module is responsible for purchasing energy from the wholesale market and supplying the charging demand of EV owners. The EV supply equipment operator should ensure the reliable supply of all charging posts under his responsibility. And the EVSE operator is also linked with the system operator in order to avoid grid operational constraints violations. The system operator can request from the EVSE operator not to further increase its demand in case the grid is highly loaded, or even reduce its requested demand in case of critical grid operational conditions. Thank you very much for your attention.
Okay, so thank you very much for this very interesting presentations. I think it's time now to open a discussion between us to exchange on this project, and so I hope everyone has been able to understand the project outputs and see the potential of fast inductive charging for the automotive sectors and the great perspectives it opens. And so, talking about this perspective, I gathered some questions about the future of the solution and the future of the FastinCharge project in general. And maybe I could ask first DBT as the project coordinator, so a French SME. What's the vision of your company in such a project? What's the added value for your company of this project, and maybe more generally as being coordinator of such an important and innovative as well as challenging project?
So for us, as a quick charger manufacturer, the FastinCharge project allows us to discover the FastinCharge project allows us to discover the inductive charging. So to make the first steps to develop this the inductive charging, and to strengthen this technology to maybe to be one day an alternative for the conductive charging.
So this project gathers private bodies, so could it be SMEs like DBT, like BATS, or larger companies like BATS, or even Fiat via CRF. But we also gather some universities, and so the question is also the same for universities, since it appears quite obvious this kind of challenging issue for a company in economic point of view. And maybe Stefan, could you tell us more about the point of view of a university for such a project, and maybe especially for FastinCharge perspective, okay, in your point of view?
Okay, thank you very much for this question. I would like to say that for our technical university, Gabro, Bulgaria, and especially for our development team of power electronics, it will be very good a chance to be a partner in this very innovative project, because our group has more 10 years experience in this inductive charging technologies for another application. For example, a leader of this of our group, Associated Professor Nikolai Majarov, has received a European project patent for another application, and when we start to work with this project, we have a lot of previously developed research results, and this FastinCharge project give us opportunity to use this result in this concrete and very actual area, inductive charging of electrical vehicles, and our ambitious is to continue to work in this field after finishing this project, and we very much hope that with some of our project partner we will continue to work and to find another project possibilities to work together, to work with companies, OEM companies. We very much hope that our coordinator DBT will appreciate our skills, and we will continue to work together.
Okay, perfect. Thank you. So as you may have seen, this project is focused on a demonstration of this fast inductive technology on a daily vehicle, but so it has to be considered as a first step for the development, the long-term development of inductive technologies. And I wanted to ask now Heitor Bustillo from BATS if there is any perspective for adapting these FastinCharge technologies, this FastinCharge technology to light passenger cars, for instance, in the future.
Yes, good question, Barthelemy. Of course, we are analyzing the matter, and we are interested on extend the solution to passenger cars. We think that this project should be only the first approach to the technology, but of course it could be improved and adapted to all the requirements to be obtained from the different OEMs. Nowadays, we are analyzing the matter with Fiat in order to know or to be sure how will it be in some of their cars, or normal passenger cars, because the point of view of a commercial vehicle is really interesting for us, but we think the future of the technology should be the more common cars, the passenger cars. So we are working in this line, and we are interested on adapt this system to passenger cars. Yes.
Okay. So there are a lot of future perspectives for these technologies, apparently.
If there is future for this technology, for sure it should be implemented on passenger cars.
Thank you. Well, imagine that these challenges will be fulfilled. That may raise some other questions about energy availability on the grid, and because sometimes the requirements of EV owners may be very different from the capacities of the grid. And maybe Yanis, you can tell us more about the role of an energy management system, for instance, to gather both EV owners' needs and grid capacity. How could it be possible to match the two notions?
Well, the EV owner will be free to choose any available charging post according to his direction or the energy needs of his or her vehicle, and he will be able to book a specific charging post at the price that has been defined in such a way in order to avoid any grid operational issues. And now, from the system operator's point of view, the system operator can reduce the demand of all the available charging posts if any operational issue from the side of the grid occurs. And he can reduce the demand of each charging post, let's say, by 10%, so that the time for charging is not considerably increased. So in this way, any inconvenience from the EV owner is avoided.
Thank you.
So I think it's time to conclude now. So I will let our friend from Technalia conclude, and want to thank Technalia for organizing this conference and having the possibility of disseminating our project.
Okay, thank you, Bart. So we have reached to the end of the webinar, surprisingly quite before the scheduled time. Thanks a lot for the participation, for the valuable contributions, interesting discussion. We hope you have enjoyed the activity, the event, and that's all on our part. We look forward to being soon with updated information on our project. Have a nice rest of the day, and that's all. Bye bye. Okay.
Thank you.
Thank you.